Hello everyone, my name is Kathan and today we'll be discussing the problem Ferris Wheel from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. There are n children who want to go on a Ferris wheel. So if you don't know Ferris wheel, it's a wheel of gondolas, and your task is to find a gondola for each child. Each gondola may have one or two children in it, so maximum a gondola can have two children in it. And in addition, total weight in a gondola may not exceed x. So there is a constraint on the maximum weight in a gondola. You know the weight of every child. Fine. What is the minimum number of gondolas needed for the children? So what you have is you have some number of children given here. So as you can see, the first line of input, you have two integers n and x, n representing number of children you have, x representing the maximum weight that you can put in a gondola. And the next line contains an integer, which is simply the weight of all child. So what you want to find is you want to accommodate this n children into some number of gondolas, and you want to minimize the number of gondolas, right? So in output you have to print the minimum number of gondolas. So the constraints are pretty modest here. N can be as high as 1e5, x and pi is also in range 1e9, and of course the weight of a children will be less than equals to the maximum allowed weight of a gondola, right? You should be able to place a child in a gondola. So here's the input test case given here. So you can analyze it in the iPad, but I guess the question is clear. You are given n children with some weights, and what you want to do is you want to you can say assign gondolas to a children. In a way, a gondola cannot have more than two children, and there is a constraint on the total weight of a gondola as well. So the total weight of a gondola cannot exceed x. Now what is the minimum number of gondolas needed for the children, right? So let's move on to the iPad and try to understand and approach this question. Let's start with the example test case first, and then we can see how to approach this question. So by the way, this is the Ferris wheel, and here are the gondolas. So you want to find out what is the minimum number of gondolas you will need to accommodate all the children. So let's take the same example that is given to us in the CSES website, which is n equals to 4. So we have 4 children, and the maximum allowed weight for a given gondola here is 10. Right? So no more than 10 weight can be accommodated on a gondola. Fine. And the weights were, I guess, 7, 2, 3, 9. Yeah, 7, 2, 3, 9. So these were the weights. Now, how can you minimize the number of gondolas? So here the answer was 3. So how this 3 came? See, the maximum allowed weight is 10. So you cannot have weight on a gondola more than 10. So 10 can be as high as, so less than equals to, right? A gondola can have weight less than equals to x. Now one gondola can be formed like this. So this is a 9 weight. Then one gondola can be, you cannot combine these two. So one gondola will be formed like this, and one will be like this. So the answer is 3. So this is how you form like the minimum number of gondolas to accommodate n children will be 3. So to summarize the question, what we have is in a gondola we cannot have no more than, you can say no more than 2 children, right? So a gondola can accommodate at max 2 children, and the weight, let's say wi, let's say weight of a gondola cannot exceed x, right? The maximum weight that is allowed for a gondola is x. Now if there is one children, that guy's weight will be definitely less than equals to x by the constraints, but if there are 2 children, the weight cannot exceed x. Fine. So how do you approach this question then? If there were no constraints, like not able to accommodate more than 2 children or the weights, what you can do is you can just take one gondola and put every children in them. So in that case the answer would be simply 1. But you have a constraint here that you cannot have more than 2 children. So at a max you will have to have 2 children. Now if you had only this constraint, what would your answer? Can you tell me? So in this case you just try to pair up every 2 possible children to minimize the gondolas. So here the answer would be what? N by 2. But of course if there were odd, let's say n was 5, then you'd have to take a seal, right? If n was 4, then you could have just made 2 pairs, so 1 gondola for each pair, so 2 was the answer. But if there were, let's say, 5 children, then 2 pairs and 1 guy will be remaining, so 3. So yeah, I mean this is the case where you don't have that weight constraint. Fine. But we have one more constraint, that is weight of a gondola has to be less than equals to x as well. Fine. But we do know that if we had only this constraint, that no more than 2 children allowed, we can, these are the minimum number of gondolas, right? Now ideally, if this weight was, let's say, infinitive, right? So in a way that when you try to add weights of two children, it will never exceed this x, right? So this x value is infinitive, then you can still achieve this, right? So what I'm trying to say is, guys, the maximum you can achieve, you can say maximum, or you can say the minimum number of gondolas you can achieve, minimum gondolas that you can achieve are actually CL of n by 2, right? And it's obvious, right? So if you can just create every possible pair, this is the minimum you can do. And when can you do that? When this maximum allowed weight is infinitive, it is as high as possible, right? So our answer will be less than this. So what we should try to do is we'll try to create as many pairs as possible, right? If one guy remains, it remains, but this is our strategy, right? Try to reach this guy. So this is our, you can say, ideal goal, but because of this constraint, it is creating problem. Fine. So because so we'll still try to pair the guys, right? So when you try to pair the guys, what wrong can go? Like you'll clearly identify that the heavy guys will create problem, right? Because if you pair a heavy guy with some other guy, there is a chance that it will exceed the maximum allowed weight of a gondola. So what do? A strategy, or you can say greedy strategy, can come to your mind is pair heavy guys with lighter guys. This makes sense, right? Why does it make sense? Any which way you have to put a heavy guy into a gondola, you're better off putting a lighter guy with it, right? So more concretely, what I'm saying is, let's say these are the weights of the children in sorted order, P1, P2, P3, so on Pn. What I'm saying is, this is the heaviest guy, right? So this, you can assume this is in sorted order. Any which way, to this heaviest guy, you have to assign a gondola. Let's say this was some weight 999, and your maximum weight was, let's say, 1000, right? So right to the demarcation. Any which way, this guy has to have a gondola. Why not try to pair it up with the lightest guy we have? So here, this, let's say this might be 1, 2, or so on, right? With this, if you put this, it still doesn't exceed the maximum weight. So then like you can save a gondola here, right? But if you don't pair up with the lightest possible guy, what will happen is this guy will consume a gondola, and what will happen is you won't be able to pair up with any other guys here. So any which way, you will have to accommodate one more gondola, right? So it's very simple. If you don't put these two guys in same, what will happen is you won't be able to put this guy with any one of them here, and any which way, one more gondola will be wasted for this, right? So that's a problem, and that's why the strategy is try to pair up the heavy guy with the, you can say, lighter guys, or the lightest possible guy available. Let's concretize this strategy with the dry run here. So let's consider this example. So these are the children weights. Now first things first, we'll have to sort the array, right? So if we sort the array, it will become 1, 2, 3, 4, 7, and 9. So there are, I guess, here 6 children we have. Now what is the strategy? Try to pair the heaviest possible guy available to us to the lightest possible guy available to us. So how are you gonna do that? So we'll need some pointers, or you can say some index variables. So this is, let's call this I, and let's call this J. Now what you want to do is you want to try to create as many pairs as possible. So how are you going to do it is, try to see if the heaviest possible guy available to you can be paired up with the lightest possible guy available to you. Fine. So can you take this 9 with 1? You cannot, right? Because if you take 9 plus 1, 10 will exceed the maximum allowed weight. So you're going to do it. So any which way, you will have to assign a gondola for this 9 guy. So yeah, fine. Let's say one gondola is assigned for this 9 guy. No problem. Maybe I can create a counter here, which is initially 0, but now it has to be updated to 1. 9, we tried 9 with 1, but we are not able to do it. So we are going to assign one gondola to 9 anyway. Fine. So we move back one step. Okay. So now this is the heaviest possible guy available to us, 7. Now you try to pair up with the lightest possible guy available to you, 7 with 1. So is 8 less than equals to 9? Indeed the case. Yeah, fine. So we'll assign one gondola to these guys. So the count is 2, right? Remember, we cannot have more than 2 children. So we assigned a gondola to these 2 guys and moved both the pointers ahead, right? So if you are curious, we assigned a gondola here, then we assigned a gondola for these guys. Fine. Right, so what you're effectively trying to do is we are trying to pair up the heaviest possible guy available to us and the lightest possible guy available to us. If we can do it, we put both of them in a single gondola. Fine. So now you have 2 and 4. Now, is 2 plus 4 less than equals to 9? Indeed, it is. You can put the heaviest possible guy available to you to the lightest possible guy available to you. So yeah, indeed. Let's do this. So we will increment our gondola to become 3, and we'll move ahead. So now I and j will become equal. So no comparison needed here. You know that if I and j are equal, then one gondola will be consumed for this guy, right? So because like this will be less than equals to x, you know that. So count will be 4, right? So how many gondolas were required here? So 2 already you are saying, one more here. So maybe I'll use a different color. So one more for these guys and one last for these guys. Right, the strategy is pretty simple. You put a pointer to the left hand, put a pointer to the right hand, and try to pair them up. If you're not able to pair them up, anyways you will have to assign a gondola for the heavier guy. So decrement that pointer. If you are able to pair them up, decrement both the pointers. Right. So yeah, I mean that's about the strategy. How will the pseudocode look then here? The pseudocode will be pretty simple. What you can do is you can sort the array. You can initialize I to 0 and j to n-1, the last guy, and we can initialize a counter here. The number of gondolas you will require to be equal to 0 as well. Now what you will do is you will run a loop. So we'll come to the condition in a bit, but you will run a loop here till of course you have only one element remaining, so I less than equals to j, we just saw. If this is the case, what you'll do is you'll first check if weight of I plus weight of j is less than equals to x. If this is the case, you do I plus plus j minus minus. That is, you put these two guys in the same gondola, and yeah, fine. But if this is not the case, any which way you will have to assign a gondola to the heavier guy. So you do j minus minus, and then you can just increment the count anyway, right? So if you are able to assign a gondola to both the children, you update the count. Even if you are not able to assign a gondola, to both, you will anyway assign gondola to the heavier guy, and then you do count plus plus. There's one little thing. What you have to do is I cannot be equal to j here, right? So if you have only one guy, you don't just add its weight and check. Otherwise, it might happen that it doesn't make sense, right? If you have just one guy remaining, you just have to do j minus minus, right? So in a way, just move one step back. In the next iteration, the loop will break, right? So this is the case, right? So I mean, you can come up with your own conditions, but effectively what you have to do is you'll try to pair up with the heavier guy with the lighter guy. If you're able to do it, it's fine. Otherwise, put the heavier guy into the gondola. Why you are not putting the lighter guy in the gondola? Because there is a chance this lighter guy can be paired up with some other heavier guy. So this is a very important thing, right? So what I'm saying is, if you're not able to pair this 9 with 1, it doesn't mean you're going to put 9 in a gondola. You're going to put 9. It doesn't mean you're going to put 1 in a gondola. You're going to put 9 in some other gondola, right? Because this 1 can be paired up with some other guy as well. There is a reason. We are going to assign a gondola to the heavier guy when the addition is going more than x. Fine. So this is the pseudocode, and I hope you have understood the explanation till now. If you did, please comment understood in the comment section of the video right now, and we can move to the coding part. So what is the time complexity here? Before we go there, the time complexity here, like there will be n log n time consumed here, and this is just order of n. You are just going through the weights array once. So this is just simply order of n log n, and the space complexity, we are not consuming an extra space, so it's simply order of 1. Fine. Alright, so here's the code. We are taking the input n and x being the maximum allowed weight in the gondola. We take the input of the weights, then we sort the weights array. I take up an index variable, I make it point to the left hand. I take one more index variable, make it point to the right hand. Initialize the total gondola count to be 0, while I is less than equals to g, while we have considered all the weights. Firstly, if I is not equal to j, that is, we don't have just single guy remaining, we check if we can accommodate both the children in a single gondola. If we can, we are going to do that. Increment I, decrement j. Else, just assign gondola to a heavy guy. So this else is for when the last person is remaining. When I is not equals to j, you just make the pointers cross. So in the next iteration, the loop will break. But any which way, you update the count. Whether you are able to assign a gondola to both guys, or just assign a gondola to heavy guy, or there was a single guy remaining, you have to assign a gondola anyway. So that's why count plus plus, and you can just output the count in the end. Time complexity, we have already discussed. It's n log n, n being the number of children here, and space complex it's order of 1 because you're not consuming any extra space. So I mean that was the video. If you understood, if you got something out of this video, please give it a thumbs up, and I'll see you in the next one.